For this review, we're going to be going over function concepts and some certain important functions. So starting with some definitions, a definition of a relation is going to be a set of ordered pairs, x comma y ordered pairs. And the definition of a function is a relation in which each x value corresponds to only one y value. So each value in the domain corresponds to only one value in the range. So that's the key thing, is only one. It cannot be any more than one. And the next thing, recall that function notation, that's pretty much what we're going to be using a lot of going forward. Function notation, we use f of x instead of y. Instead of the dependent variable y, we use the function notation f of x. We could use g of x, h of x, and anything else. Typically, we just use f of x for function. And evaluating a function using function notation, if we're given a function, we can find the xy ordered pairs by just plugging in the x values and evaluating. So for example, let's say we have f of x is x squared plus 3x plus 5, and we want to evaluate f of negative 3. We know that all we have to do is just plug that right in. Plug in negative 3 into all of the x's. Make sure you use parentheses when you're plugging it in. And then you just have to make sure that your order of operations are correct. So that gives us negative 3 squared, 9 minus 9 plus 5. That gives us 5. So the y coordinate's 5. So we know that that corresponds to an ordered pair of negative 3 comma 5. Next one for b, we're evaluating f of a. So all we have to do is plug in an a everywhere that there is an x. So that's a squared plus 3a plus 5. And that's actually it. We can't simplify it any further. We essentially just kind of swapped out the variable. Next one, f of negative x. Plug in a negative x everywhere there's an x. Negative x squared plus 3 times negative x plus 5. And then you have to simplify it. So simplifying it, negative x squared is positive x squared. Negative x times negative x minus 3x plus 5. Remember, we did this, we plugged in negative x to help us determine symmetry. And last one for d, f of x plus 3, a little bit harder. We have to plug in an x plus 3 everywhere there's an x in the original. And as long as you do it with parentheses, you should not mess it up. So it's x plus 3 squared plus 3 times x plus 3 plus 5, and you have to simplify it. So simplifying this, x plus 3 squared, remember you have to FOIL that out. You can use the shortcut. It's going to end up being x squared plus 6x plus 9. Okay, so I just did the shortcut version in my head. And then for the next one, for 3 times x plus 3, distribute the 3, and then plus that 5 at the end. And combine like terms, we get x squared plus 9x, 18 plus 5, 23. So x squared plus 9x plus 23. Okay, one more example for this. We have g of x is the square root of x plus 3 minus 2, and evaluate g of negative 7. So we plug in a negative 7. Negative 7 plus 3 minus 2, the square root of negative 7 plus 3 minus 2. Evaluate what's under the square root. That gives us negative 4. The square root of negative 4 minus 2. And staying with real numbers here, the square root of a negative, that gives us imaginary numbers. So I'm going to say that this is out of the domain, because we did not end up getting a real number out here. Okay, and then negative 3, g of negative 3, plug that in, square root of negative 3 plus 3 minus 2, and we know that negative 3 plus 3 is 0, square root of 0 is just 0, so we get negative 2. All right, next thing, we are finding the intercepts of a function. The two different kinds of intercepts are going to be the y-intercept. We find the y-intercept when x is 0, and then the x-intercept we find when y is 0. So it's opposite. Y-intercept x is 0, x-intercept y is 0. And just know that the x-intercept is also called the 0 or the root of the function. Okay, so let's go ahead and do some examples. So like I just said before, finding the x-intercept, let y equal 0, solve for x. Finding the y-intercept, let x equal 0, and solve for y. First one, let's find the intercepts for f of x equals 6x plus 2. Automatically, we should know this is a linear function, and we should have an idea of what it looks like in our head. So let's find the x-intercept first. So this is when y equals 0. So that's going to be 0 equals 6x plus 2. Remember, f of x is the same as y for this purpose. So now we have to solve this for x. So solving it for x, we subtract 2 on both sides, divide both sides by 6, and we get x equals negative 1/3. So that is the x-intercept when we simplify that fraction. And now let's find the y-intercept. Finding the y-intercept, we let x equal 0. So that's going to be 6 times 0 plus 2. So notice I just changed f of x to y here. And that's going to be y equals 2. So 2 is the y-intercept, which we should have known because this is in y equals mx plus b form. B is 2, which is always our y-intercept. Okay, next one we have y equals x squared plus 6x plus 5. Let's find the x-intercept. Find the x-intercept by letting y equal 0 and solving for x. And now we recognize that this is a quadratic equation, so we're hoping that it factors, and it does factor. It factors to x plus 5 times x plus 1, and you set each one of those factors equal to 0 separately and then solve them, and we would end up getting -5 and -1. And next, for the y-intercept, we let x equal 0, and hopefully you can do this in your head. I recommend doing it in your head going forward. I'm just going to write it out. You let x equal 0, that cancels those first two terms. You get y equals 5 as your y-intercept. Okay, moving on to the different ways that we can represent a function. So there's 4 main ways that we can represent a function. The first one is verbally, and that's just saying it with words. The second one is numerically, which is with a table of values. The third way is visually with a graph. Fourth way is algebraically with a function. Okay, we're not really going to use verbally a whole lot. Same with numerically, we won't even use that a lot. Typically, we're going to be using visually and algebraically, graph and function. Okay, let's take a look at this example. Let's create a table of values and a graph for y equals 3x minus 2. So we're given it as a function. Let's create a table of values and a graph. Let's do the table of values first. So table of values means the x and y values. So we can pick whatever values we want. I'm going to pick just a couple of them, -2, -1, 0, 1, 2. So we pick the x values because that's the input, and we see what they give us as an output. So for the y values, we plug these in, plug in the x values, and evaluate. That gives us -8. And we do this for all of them. And this is what we should get when we get all of them. And notice that these are all increasing by +3 as we go along here. That's because all of the x's are increasing by 1, and the slope of the line is 3. It's the rate of change. Okay, let's graph these now. Let's go ahead and graph them on x, or xy plane here, the rectangular coordinate system. So 1, 2, 1, 2. And I just went down to -8 and up to 8 on the y-axis. So the first one is -2, 8. -2, 8 right down here. -1, -5. 0, -2. 1, 1. And 2, 4. and we connect them. We knew the graph was going to be a line, and we label it. Okay, so now going over some of these important functions that we're going to be discussing and using in calculus. So I'm just going to mention these very briefly. I'm going to kind of fly through this. But the important functions are going to be linear functions, quadratic functions, polynomial functions. And we know that linear and quadratic functions are also polynomial functions. And then there's rational functions, trig functions, exponential, logarithmic, algebraic, and power functions. Okay, now we're just going to dive into each one of these very, very briefly. So for linear functions, we know that these are first degree polynomial functions, and they can be written in the form f of x equals mx plus b, or y equals mx plus b, where m is the slope and b is the y-intercept. So m and b are numbers, m is the slope, the rate of change, and b is the y-intercept. And assuming that the slope is not equal to 0, the domain and range of all linear functions is negative infinity to positive infinity. And obviously the graphs of linear functions are lines, which is why we call them linear functions. So here's an example, y equals 3x minus 2, what we just did. It is a line. Okay, quadratic functions is next. Quadratic functions are second degree polynomial functions. They can be written in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers. And the domain of quadratic functions is negative infinity to infinity. The range of the functions will differ depending on what a, b, and c are. And here are some examples. We kind of generalize them in two categories, if they're opening up or opening down. And the one on the left is opening up. And what we're going to be calling that in calculus is concavity. We would say that's concave up. And we see the one on the right is opening down, and that's what we call concave down. Okay, so that is concavity, and those are kind of the two basic kind of quadratic functions. Okay, next one, polynomial functions. So in general, polynomial functions, we just did linear and quadratic. Those are first and second degree polynomial functions. Now polynomials in general here, this is what the generic version of a polynomial function looks like. A sub n, x to the n, plus a sub n minus 1, x to the n minus 1, all the way down to plus a sub 1x plus a sub 0. So it looks confusing. But all this is all of those a's are just numbers, and n is a positive integer. So we have to remember that these are real numbers. All of these coefficients in that last constant term, they are real numbers. And all of these exponents, well, not on the constant term, all those exponents are positive integers. No fractions, no negative numbers. Okay, so that's all a polynomial function is. The domain of a polynomial function is negative infinity to infinity. We can plug in any value. It won't break any math rules. And here are just some examples of them. It gets more and more complicated the higher degree that we have. Something that's very important is polynomials are smooth and continuous functions. Smooth meaning no sharp turns. And whenever there's a sharp turn in a graph, the sharp turn is called a cusp. And these are also continuous. Continuity, I'm going to use the kind of bad definition here. And I'm going to say that continuity means you can draw the whole thing from left to right without picking up your pen. So there's no jumps, there's no holes. You can draw the whole thing without picking up your pen. We're going to get to a much better definition of continuity, and it's going to have to do with limits. Okay, so you can see in these diagrams here, A is starting off with a cubic, B is starting off with a degree 4, C is starting off with a degree 5. So you can see the higher the degree of the polynomial goes, the more and more possible turns it can have. Okay, so that's pretty much all I'll mention on those for now. Just notice they're smooth and continuous. Next thing is rational functions. Rational functions are of the form f of x is p of x over q of x. The important thing here, because it looks kind of weird, like it doesn't mean anything, is that p and q are polynomials. So rational functions are a ratio of polynomials. And we know that ratio means fraction. Okay, so the domain of a rational function is going to be all real numbers except the x values that make the denominator equal to 0. The values that make the denominator equal to 0, because we can't divide by 0, right? Those x values that do that are either going to be a vertical asymptote there or there will be a hole there. So it gets a little bit more complicated with rational functions. And when graphing these rational functions, like I mentioned, there could be vertical asymptotes, there could be holes, there could also be horizontal asymptotes or slant asymptotes. It gets a lot more involved with these graphs, so I won't get too into it. But vertical asymptotes, we usually represent them as you see here with a dotted line. That just means the function values are going to go to infinity or negative infinity as the x value approaches a number. So they're not actually part of the graph, it's just representing the function blowing up to infinity or blowing up to negative infinity. Okay, so I'll move on to the next thing. Trigonometric functions. We're going to be working with trig this semester. So the trig functions that we use are sine, cosine, tangent, cosecant, secant, and cotangent. And we know that we abbreviate sine, S-I-N, cosine, C-O-S, tangent, T-A-N, cosecant, C-S-C, secant, S-E-C, and cotangent, C-O-T. Okay, and then when we use them as a function, like if we're looking at sine as a function, we would say y, or f of x, equals sine of x. It's implied that x is the input. So you're never going to see like just y equals sine just by itself. It needs some sort of input or else it just doesn't make any sense. Okay, and hopefully we remember the reciprocal identities. Sine and cosecant are reciprocals, cosine and secant are reciprocals, tangent and cotangent are reciprocals. And also remember, reciprocals is not the same as inverse. All right, radians. So onto radians, and hopefully we all remember radian measure. Radians is always used for angle measure in calculus. So we're not going to be using degrees, we're only going to be using radians for calculus. And for sine and cosine, the domain is negative infinity to infinity, and the range is -1 to 1, including -1 and 1. I only have the graphs of sine, cosine, and tangent here. I recommend looking up the other three as well. So sine, the first one here, sine and cosine look very similar, right? They're both just, it looks like this wave that goes on forever from negative infinity to infinity. That's because they basically are the same. It's just that they are horizontal shifts of one another, or phase shifts of one another. Okay, so typically when we think of sine, it's good to think of it from 0 to 2 pi. And we should kind of have that image in our head. If we know what that looks like, then we know what the rest of the whole entire thing looks like because of symmetry. That's the period of the graph, and it just repeats itself over and over and over again. Same thing with cosine. If you know 0 to 2 pi, that's the period. It repeats that shape over and over and over again. Okay, and then tangent, we should also know that tangent, using the quotient identity, is sine of x over cosine of x. That will help you graph it. It looks like this, and it does this forever. It keeps on going with that shape over and over again from negative infinity to infinity. Okay, so these are periodic functions. They repeat themselves forever. I'll end it there for trig though, or else keep on talking about that forever. Okay, exponential functions. Exponential functions is when there is a variable in the exponent. So that's something like f of x equals b to the x, where b is positive and not equal to 1. So notice that the variable is in the exponent this time. So b has to be positive. If you have a negative 2 to the x, let's say, try plugging in some values for that and see what happens. It doesn't end up being an exponential function. It ends up being a collection of dots, and it looks pretty interesting. So make an XY table for that if you want and see what it looks like. If b was equal to 1, if we had b to the x, 1 to the x, that would always equal 1, right? So that's not exponential, that's a horizontal line. Okay, so there are, well, before I mention that, the domain of an exponential function in the form b to the x with nothing else being done to it is negative infinity to infinity. We can plug in anything for x. The range is 0 to infinity. And it always helps being able to imagine the graphs of all of these types of functions. So there's two types of the graphs that you should think of. If the base is greater than 1, then it's an exponentially increasing function. So in this example, we have y equals 2 to the x. If you plug in x values, it's going to get larger and larger. The function values are going to get larger and larger as x gets larger and larger. And then second, if you have the base is between 0 and 1, like y equals 0.5 to the x, then it's an exponentially decreasing function. Okay, so I definitely recommend creating your own little XY table for this, and just plug in some x values and plot it and verify that's what happens. Okay, and for both of these, there's a horizontal asymptote at y equals 0. So it never actually crosses the x-axis. It gets asymptotically close to it, infinitely close to it, but never touches it. Next one, logarithmic functions. Logarithmic functions are inverses to exponential functions. So they're called logarithmic because it's a kind of a play on words. It's like logos and arithmos, I think in Greek. It means like a ratio of a number, which is essentially an exponent. So that's, let's say if we have like log base 3 of 9, that's a number, log base 3 of 9. What that means is, what do we have to raise the exponent, what do we have to raise the base 3 to in order for it to equal 9? Well, this equals 2, and that is because 3 squared equals 9. Okay, so make sure you know how to convert between exponential form and logarithmic form there. And what we have here for the function form of it is f of x equals log base b of x. Make sure you know how to read it like that. That b, the base, is a subscript, and the x is the input to the log. Okay, and b has to be positive, and it cannot equal 1 for the same reason, essentially, as the exponential on the previous page. The domain of log base b of x is 0 to infinity, and the range is negative infinity to infinity. It is the complete opposite as the exponential function. Domain and range are flip-flopped for inverse functions. That's why it's completely interchanged. Okay, example, just like exponential, log has two main types of graphs here. If the base is greater than 1, then it's increasing, so that would be something like these functions over here on the left. You can look at the different bases and compare. If the base is between 0 and 1, it is decreasing, like this graph over here. I use the base of 1/3. Okay, and then there's a vertical asymptote. Whoa, a vertical asymptote at x equals 0, which is the y-axis. Okay, so that's logarithmic. Next one, two more, I think. Algebraic functions. Algebraic functions are kind of like a mixture of things. It can be constructed using addition, subtraction, multiplication, division. And then the big one is or taking roots. So square roots, cubed roots, rational roots, rational exponents. So here are some examples. These ones just kind of can look completely different from each other. So the first one is x times the square root of x plus 3. It looks like that. Next one is the fourth root of x squared minus 25. And next one is x to the 2/3 times x minus 2 squared. So you can see they look completely different. Domain will be affected a lot with these ones. So I'll just kind of end that one there. And moving on to the last one of power functions. So we're going to be referring to power functions in the next few weeks using a certain calculus technique. And power functions are one of the easiest functions, thankfully. It is a variable to a number. So f of x equals x to the a, where a is a real number. So it's not considered a polynomial, a power function, because polynomial is only positive integers, positive whole numbers, whereas this could be fractional exponents. So here are what I broke it down into 3 little cases here. If a is a positive integer, so that's something like what we have down here, x to the first, x squared, x cubed, x to the fourth, x to the fifth, and so on. That would actually make it a polynomial, right? Here are the graphs of the first 5, and then it could keep on going. But the first 5, we have y equals x. We know that that's a line, x squared, quadratic, x cubed, cubic, and then it continues. So those are for when the exponent's a positive integer. Then it gets a little bit harder. If a is a fraction, where n is a positive integer, 1 over n, so it's 1 over a number, 1 over 2, 1 over 3, 1 over 4, 1 over 5 is the new exponent. Then we have these root functions. So here is the square root, which is x to the 1/2. Here is the cube root, x to the 1/3. And then if you want, keep on graphing x to the 1/4, x to the 1/5, and so on. Last one, if we have a to the -1, or sorry, a equals -1, so x to the -1, we know that a -1 exponent just essentially means reciprocate the base, 1 over x to the +1. That is a rational function called the reciprocal function. So that one looks like that one right here. Okay, so those are pretty much the 3 main types of graphs. If a is a positive integer, if a is a fraction, or if a is negative. Okay, so either way, those are all technically power functions, and once again we'll see that in a little bit. Okay, so that was just a very quick review of several very important functions.